Sorry about that. Yeah, I'm Vishu Booshan. I'm part of the ZHA Architects, part of the computation and design group there. A bit about myself. The thing works. A bit about myself. I'm part of the computation and design research group there, where I co-lead the team with Booshan and Niels Fischer and Henry Louth. I'm also a lecturer at the UCL at the Bartlett School of Architecture in London. On a day-to-day basis, we kind of do these 3 or 4 things, which is to research in computation and design, and also to write and disseminate this knowledge first within the office, but also widely through workshops around the world. A bit about the team, core team, an acronym for computation and design, started in 2007 by Niels Fischer, Booshan, and Patrick Schumacher, who is the principal. It started off as a project independent research group, looking at geometry processing and also looking at then digital manufacturing technologies. And as the research has matured over the period of time, over the last 15 years, like the kind of projects we are doing in the company has also changed. As you can see, early on, we were doing like smaller scale projects. And as the technology has matured, now we are able to apply the same to larger scale projects like stadiums, infrastructure projects, museums, etc. The team is currently made up of 22 people. Mostly all of them are architects with interest in computation, varying degrees of interest in computation and design. Some people more interested on the compute side, developing tool sets. More others are more interested on the design side, how to use computation in application of early stage conceptual design. The research strands we have in the team is looking at these 4 things or 4 strands, looking at high performance geometry, game tech and participatory systems, future twins, and machine learning and AI. Hopefully, I'll cover a bit of each of these topics in the presentation. Typically, each of these strands go through these 4 steps, where you start off as a project independent research, develop toolkits, and showcase its application in what we call pilot projects or special interest projects. And then once the tools and the technology are robust enough, they get applied to larger scale commercial projects in the office. So the presentation is structured as follows. We'll talk a bit about the framework which powers all of this, looking at what are the current technology demonstrators we are working on, specifically focused on digital concrete. Then we look at aspects about how we are making these what we call participatory systems using geometry for all, and also future twins and AI systems. So the spatial technology stack, what is it? We call it Z-Space. We all believe that architecture is a cultural production enabled by technology. It has been the case since the beginning of times. Like even if you look at Gaudi structures, we're always blown away by the spatial qualities and the visual imagery of the spaces. But there has always been a technological remit which is powering it. In this case, looking at graphic statics, masonry structures, so on and so forth. Same is the case with computer graphics and animation industry. So we're always blown away by the visual aspects of these CG movies. But if you look a bit deeper, the technology supporting it, as was explained in most of the presentations today, is also very novel. And these could be easily be adapted into architectural design as well. So we as a group, when we started looking at the framework, was to look outside our lamppost. So we are all mostly architects, and we didn't want to find solutions mostly within our remit, but actually to look at someone else's lamppost so that we can borrow and build upon what's already there. So what can we borrow from animation and the computer graphics industry? These are the technologies looking at computational geometry, but a subset of it, which is called architectural geometry in architecture. Game technologies, you can borrow that for multiplayer systems and designing for choice. We'll take a look at it as the presentation goes on. You can also look at file formats like USD, which has been around by Pixar for the last 30 years or so. You can now access those things much more easily through NVIDIA's Create Kit. And the same goes with AI as well. There's like a lot of foundational models we can borrow, and then we can build on top of it what are the architectural applications we want to build. So basically, a spatial technology stack is a combination of these divergent spatial technologies, which includes architectural geometry, game technologies, and AI. And the framework itself borrows from wide amount of research happening both in academia, but also in industry, in technology companies like NVIDIA and uh, Autodesk, etc. The spatial technology stack, as we currently have it, covers both content creation aspect, where typically we have been involved in early stages of design. So it involves a lot of geometry processing, creating tools for amenable for robotic and digital manufacture, like 3D printing. And it also looks at later stage delivery of projects where we are in schematic design and DD. And in between is the game tech, which is powering all the configurators, uh, integration of our tools in games, etc. The stack is also independent of the softwares we have in the office. So you can see a wide range of softwares we use, right from conceptual, being it Autodesk Maya, or to delivery of the project in Revit, Rhino, and now also looking at Omniverse, Unreal, etc. Uh, so looking at the first aspect of high performance geometry, like I'll take you through a project which we have been, it's a collaboration with the block research group at ETH, who are researching into masonry structures, and Incremental 3D, who is a robotic 3D manufacturing company, along with Holcim, who were the material researching a company looking at creating custom inks for 3D print. So when we started out the project or the collaboration, we were trying to bring up a new language for concrete, using wisdoms of masonry and adapting it into digital technologies of manufacture. The goal was to have these 3 Rs, which is to reduce the amount of material required, reuse the blocks which were printed, and recycle by doing material separation. All of this was achieved through what we call strength through geometry, trying to reinterpret masonry structures using 3D printed concrete blocks. So you can think of these blocks as synthetic blocks or synthetic stone. And this is possible because you're aligning your systems or the geometry into the structural force actions. And this was all made possible through an integrated design to production pipeline, where we as designers, structural engineers, and fabricators were all able to collaborate in one platform. And that platform considers the file format you see on the right. As each and every step is being done, a schema or additional attributes are added into the file format. So this includes going from generation of the geometry, the structural performance using form finding, then looking at stereotomy of the blocks, splitting them into 100 blocks or 50 blocks, and it right towards the end of the G code of each of the blocks. It can also store schema. The schema also enables you to store the sequence of assembly, what should be the uh, scaffold in this case, which was one of the items of research we continued further. So what was useful about this was we as designers, we could make changes on the design till the last day, till the robot was press play on the robot to print the blocks. And this was printed by Incremental 3D in Innsbruck. On site, this was for the Binale project in Venice. So all of the blocks were shipped over. So some of the blocks were as big as 2 meters um, in height and 2 meters in width. And these were then assembled one by one on site. So you can see in this case, we had to use a single-use scaffold waffle structure. This was done so because of lack of time at that time, but this was subsequently researched in the next version, which was a more permanent version of the bridge. So in this case, you can see there is these neoprene pads, which are giving in friction. So there is no glue holding these blocks together. Once the last keystone goes in, it performs like an arch. the whole structure is standing in pure compression. So this enables it to be, the material is separated. So if you want to dismantle it, it's easy to dismantle, take it away and assemble it somewhere else. Learning from these, the mistakes or from the things we made in the first version, a more permanent version was done for whole sim to look at what is the long term. They wanted to research about how does the material perform over a period of 5 to 10 years. So a permanent version was created called Phoenix. So in this case, we were looking at circularity of construction. So as I said, the materials were disassembled, and the same material was used to recomposite and build the new blocks of the new design. The design was changed to accommodate all the variations and updates we could think of, both in structure and fabrication from the first version, but also showcases that the material could be reused. In the first version, we used steel as the foundations, and that steel was used in some other project, not in this one, because and the concrete material itself was reused in this current project. So the improvements we made was to again try to reduce the amount of material required. So we went back and tried to look at the bracing strategies. And then the more important change was to reduce single-use scaffold systems. So you can see the image on the left has more timber waffle material, but on the right, we were trying to use mostly reusable steel scaffold. But because it's a double curvature geometry, you still some amount of waffle structure, but the amount of wood used from version 1 to version 2 is about 50% less. And all of the material which was used in the previous version was recycled and reconstituted into the new blocks. The new blocks in this case were also made slightly smaller so that it's easier to ship and also to assemble. And previously in the first version, we assembled one block at a time. But in this case, there were like 6 or 7 blocks which were assembled at one point and put on in the correct position. So this technology is now getting more widely accepted, and this is getting continued onto. Okay, the video doesn't seem to work, but we are building hydrogen stations for NAT power, which is using the same technology to build hundreds of these stations in the Mediterranean. Okay. The link's great. Yeah, so the research is actually being continued forward, looking at 3D printed with now looking at carbon negative concrete. So this is a research we are doing with other collaborators, specifically UE, University of Ghent, where we are trying to build up a mix for 2K mix for carbon negative and carbon neutral concrete, and then showcase its applicability in architectural build systems. And these kind of research we kind of develop further with other technology demonstrators and other collaborators as well, looking at fabric formwork for concrete, robotic hot wire cutting, uh, thermoplastic printing, so on and so forth. The next aspect we wanted to show was called geometry for all. The things we showed previously, looking at developing custom tools, custom research, predominantly at the initial stages are very expensive because a lot of time goes into creating these tools, researching them, making tools applicable to design, so on and so forth. So this has been, as you can see, looking at tensile structures, 3D printing, hot wire cutting. All of these novel technologies take a time to understand and build custom tools for design. But at the same time, we saw benefits of looking professionally generated content or PGC is because they're immersive, they're spatially coherent, and spatially very interaction rich. We also saw in the previous project there are structural benefits, there are material benefits, and they are high performance. So you can use lesser materials to do the same geometry. So these are all the benefits, but at the same time, there are like a lot of, they're expensive and time intensive to make. So, and this is why we are kind of looking now at user generated content, which is using tile sets which are procedurally generated. So once you have sections of architectural component, then you can use the crowd to create variations and multiple options. So this was done for a collaboration with UEFN or Unreal for Fortnite, which is a game for shooting. But then now it has been, they opened up Unreal for Fortnite creative developer. So they were collaborating with us where we created these kind of tile sets to create a game system for districts in London. So this is like some of the tiles of where of a mixture of residential buildings, office buildings, so on and so forth, and then trying to mix that with the land use available in London and reimagining the city or by developing certain districts in London. This game was launched in September, like a month ago, and currently it's still available. So if you guys are interested, please log in and play. So this is an instance of people using the game setup to create their own offices, own landscapes, and each of these has a score attached to it. If you're making good designs, you get a higher score. If you are making random things, there is no negative score, but you have a lower score in this case. So this is enabling a lot of people to create. So making, we are also trying to integrate this into educational platforms so that more architectural students can have access to it and develop these geometries and then subsequently set up the gameplay as well. You can also extend the same technologies further into architectural platforms. In this case, a systems design for architects, engineers, fabricators, etc., to create a kit of part, which is already structurally informed, which is also fabrication-wise informed. So once these systems are developed, you can then procedurally generate a combinatorics of what the units could be. So in this case, you have 5 types of floor slabs, 5 types of balconies, 5 types of facades, and there are n number of options you can create just with these minimal 5 types. So at the same time, because it was done in collaboration with the fabricator, you can also track cost on how much is going to take to build. And if you're an end user, it will also show you cost of how much it's going to cost for you. So this was then integrated into a web platform. Uh, where the end user who's going to live in that community could actually choose where they wanted to be. So in this case, a gameplay was set up where they could use or choose voxels where they wanted to be. Then they can choose what kind of units they want and how they want to customize their own units, whether they want a 2-play unit or a wide unit, or 2-bedroom unit, 1-bedroom unit, so on and so forth. This also enables for an interesting gameplay where if I and someone else wants the same location, uh, then they have to bid with each other to see who gets the plot. Once these geometries are already integrated into the web, then the natural next step was to put it in metaverse or what we call as future twins. So we are currently building a ZHA city inside of the metaverse called Metrotopia, where we are also collaborating with other architects to kind of showcase their content in these kind of exhibitions. It also enables to format files to be put on the metaverse. We all do the optimization as well. But the city itself is also showcasing designs which are unbuilt by ZHA or ZHA, and that's also part of the landscape. And so it's for people to come in, have meetings as well. Like a lot of the clients, we take them into the Metrotopia and showcase various typologies of buildings we have done so far. So it also gives them an immersive experience. And all of this is kind of currently being developed. We also do these future twins for buildings which are not yet built. That's why we call it future twins. for the Bayaboo residence we just saw, or landscapes or master plans. You can also simulate how the city is going to develop over a period of time. And if it is virtually feasible, then you can build it in the physical world. So this is heading to a paradigm of what we call design once, use twice. So you design using the same technologies we have, you design the building first for physical realization, in this case, a stadium. And then second, use the same geometries. You don't need to rationalize it because they're already rationalized for both the use cases, and then put it on the web. And in this case, this is also a metaverse for the stadium the client wanted, so that they can, the home fans can actually enjoy the stadium in the web as well. Moving further, looking at AI and machine learning. So diffusion model, like most of the people in the room, or everyone's familiar with diffusion model. So we also started with the same, looking at how to augment existing foundational models with data sets from our 3D model, our photographs of build projects, and also renderings, and try to develop a trained model to generate outputs similar to the work of the office. So these were some initial outputs. This is again almost 2 years ago. Technology has developed much rapidly since then. But these were some of the initial outputs we were able to generate after training with custom data. Subsequently, we have developed multiple LoRa models using our own data sets, looking specifically at facade systems, master plan, interiors, and graphics. And it's now being showcased to use like in early stage design assist. So where you can create ideations for master plans or ideations for facade systems. So you can combine multiple LoRa's you have and give ideation. So again, still this is only images, but still it's used in early stages of the project. It also generates, we are also being commissioned to do NFTs. So in this case, this was one of the NFTs we did for one of the museums who were our prior clients, which creates, they wanted to showcase multi-materiality of the museum they built. And these were some of the things which were coming from the LoRa models I just showed. So how is it getting used in the design is like it's integrated into platforms we use like Rhino and Maya. So as the designer is designing on the right, they're able to get a visual feedback of how it's spatially performing as they go. And similarly, you could also call in stable diffusion models and other models in AI, in Maya. Same thing happens with McNeil's Rhino. What we are currently doing for that is to kind of, how can we teach tectonic aspects to AI? So typically, this was the workflow, right? You have an image on the right, which is a depth map or a normal map, and then you generate something on top of it. What we're currently trying to do is like, how can we embed some other information, even though it's just an image? How can we embed other informations like structure or fabrication related, material wise related, or environmental related things? So what we are currently doing is based on the models we have from the various architectural projects, we pick out the structural systems and tag them. So you can see on the left, which says what kind of structural systems, those become tags. Similarly, materials become tags, and the environmental things like balconies facing north side or south side, all of them become tags, which you can prompt later on. So this was a workshop we did at Digital Futures, where we are kind of exploring that trained model set and how, what are the current kind of outputs coming out of it. This is still very early days. We were also testing out early 2D image to 3D, but this still, so this is still showcasing the 3D models and the data sets which were used. And subsequently, you'll probably see the results coming up in the diffusion model. Yeah, the training of all of these actually was done in like about 30 to 40 minutes using the hardwares from NVIDIA, and it was done on the AWS. So these are some of the outputs you get based on the trained models and the prompts you give. So in this case, we were looking specifically at towers. Uh, And as I said previously, so it requires good RTX cards to actually speed up your training process, but the whole training takes about 30 minutes to do. But this is not where we want to be, right? Like we want to move away from just generating images. So we started looking at how if we can predict structural simulations like topology optimization, which are like finite element analysis, which takes a long time to set up and run. So the compute time taken for these is typically 30 minutes to 35 minutes to, which includes setting up the model. But these are not the case when you're trying to at early stages where design is in flux. So when design are in flux, even predicting models which are 60% accurate or 80% accurate is actually much more feasible. And if it is quick time, it's much more feasible to have that model rather than a much more accurate simulation. And this is, in this case, we are trying to predict by learning from geometrical features. So from all the analysis we have done previously, trying to attach it into learning from geometrical features and predict them. And you can see it's giving, in this case, it's still only a chair, but now we are applying it for architectural buildings. What we are also doing is to kind of tag these data sets we have from projects within the company. So all of the procedurally generated content is becoming structured so that we can attach procedural generation of these geometries into a large language model to learn from, to see if we can generate more sequence of operators for creating geometry. So hopefully using foundational models, which are now publicly available, as George was saying in their NIMS platform, combined with our data sets, we want to create AI assisted spatial tile sets using prompts. So all of these tools are coming together in one platform called ZSpace Kit, which is built on top of the Omniverse Kit app, where we are trying to create a collation of geometry and tool sets. So in this case, showcasing some applications in a stadium project where each of the designer is kind of working in the platform of choice, whether it is Maya, Rhino, Revit, so forth. It's enabling us to do lot of large scale projects, bringing them into Omniverse so that we or I as a project manager just have to go into one file and look at all the updates. I don't have to go to individual platforms to look at it. And there are like a lot of native connectors to this. If not, we build up the connectors, in this case, building our connection to our own platform so that we can also do optimization related tools. So now you can integrate different tools from which are specific for which are done specifically in a specific platform. Uh, yeah, anyway, like in this, what it's enabling us to do is to the designer to use tools from multiple platforms which are good for those things. So if you want to optimize and rationalize things, there are tools available which might be performing much better than in Rhino. So then you can send the schema out, optimize it, and then get it back. So the schema is enabling us to use platforms for its best performance. The integrated platform is also enabling us to create or quickly iterate through multiple options because you have feedback from the structural engineers or the facade engineers, so on and so forth. It's also enabling you to negotiate while you're designing with the structural engineers or the fabricator to push back as designers to say, okay, there are alternative options we can explore because all of them are in one collective platform. It also enables you to transfer information between designer and fabricators very quickly because it's, again, you're trying to track down all the procedural nature of the geometry in its creation itself. And the schema already embeds all of this information. So it's very easier to create all the geometry method statements for each of the projects. Once integrated, you can also use GPU computing, in this case, looking at sign distance field, which was done for creating all the print paths, which I showed for the project previously. And you can also embed other informations like structural simulation aspects. Again, the GPU here is enabling you to do about 60x acceleration, where as the designer, you're making modifications, you're already having information about the energy consumption or the solar radiation. In the previous step, you could also do structural things in a similar way. So all of these tools are kind of enabling to augment designer intelligence and to support them in making an informed decision. What it's enabling is to create parallel, uh, at least overlaps between the various sequence of stakeholders you have in an architectural project. It's not fully parallel, like, but even if it is like 5 to 10% as a conservative estimate overlap, you save quite a bit of time. Uh, and what's not here, you can see the construction is on the outside of that. uh, that's also something, and there is scope for improvement. So if the construction aspects are also integrated in large scale projects, then you'll be able to quickly iterate and make a much more robust delivery of the project. What this enabling is to us to quickly iterate through and also deliver on a lot of similar typologies. So these were like 6 stadiums we did in the last 2 years, and all of them were powered by similar kind of tools. So we didn't have to rewrite any of the tools. The same tools were applied on multiple projects. And not only a single typology, we are doing that for multiple typologies like stadiums, master plans, residential buildings, so on and so forth. So in summary, uh, so we saw what the spatial technology stack is, where it is borrowing from all the scientific knowledge, but also how it's getting applied into larger scale architectural projects. And these kind of spatial technologies getting accelerated with a lot of startup businesses, which were initially, when we start developing the framework, were all startups. Now they're getting scaled businesses, but a lot of design teams are also investing into these kind of prototyping labs within their environment. So it's like a lot of knowledge transfer happening there. Um, Again, as I previously mentioned, spatial tech is accelerated by introducing crowd into the mix. So you're generating using crowd or crowdsourced data or crowdsourced geometry. It's being accelerated by using AI and also hardware technologies. And it's being accelerated by all the foundational models and all the tools now are available for a lot of people. So we don't have to actually make new tools. There are already existing tools out there which are open source, which you can use and embed into your workflows. So you don't have to wait for it to be embedded into the platform of choice. You can just use standalone things and build up workflows based on that. And it's the USD format itself is getting a lot of attention through the founding partners, but a lot of architectural companies which are also in the with us here today are also part of it to drive the AEC side of USD, and that will enable us to accelerate that as well. So it's a very exciting time. So let's collaborate to augment intelligence, which will hopefully disrupt the AEC technologies. Thank you.